Yeah, I got an interesting back-to-back of shows today.
Who else are you talking to?
Um, I have a gentleman coming up. What does he do? He's a climate philosopher
Oh,
slash, wouldn't call him a scientist, but he makes a moral case for fossil fuels. So
wow.
yeah, yeah. I don't ever limit the amount of people we can talk to on the show, or let them bring their case, and let's see, let the good ideas rise to the surface. It's needed. But welcome to the Bus Driver Experience, everybody. If you're watching this on YouTube, welcome to the show. This after the case. Welcome to the Bus Driver Experience. I'm joined by physicist, mathematician, theoretical physicist Matthew Leifer from Chapman University. Matt, what's going on today? How you doing?
I'm good, thank you. How are you doing?
Pretty fantastic. Sucks we're in a global pandemic, but I'm,
Yes.
I'm actually pretty happy that everybody's treating it pretty well. Everybody's not freaking out too much.
Yeah, it could be worse. Things aren't too bad here in California. I think we've had pretty good leadership, at least here.
Yeah, we've everybody puts even negative connotations on the Trump administration, but I just don't think anybody really knows how to has experienced a pandemic. It's something we haven't experienced, at least in our generation, in our time, and trying to act and counteract the best situations possible. Luckily, I think our governor here has done a great job doing what we can do with it. But people are getting antsy, people are freaking out, and
Yeah.
but this is reality. This is the universe that we live in. Yeah. the,
Yes.
uni- the universe we seem to blast off into. But I'm glad I got to talk to you, because it's just really interesting. I would love to hear your take as a physicist, mathematician. How are you looking at the world? How are you looking at reality itself during a pandemic and everything happening?
Yeah, well, it's kind of, it's weird because, the research I normally do is like fairly abstract, fairly, esoteric to some people. And there I am, sitting teaching classes on Zoom or whatever, and talking about, the fundamental nature of reality. And in the back of your mind, you're still thinking, well, we're in the middle of a global pandemic, and people are dying, and I'm a scientist, so what am I doing talking about the nature of reality? But that's what I decided to specialize in.
Mm-hmm.
And I think that most scientists in this situation have a sort of a natural, as a scientist, you want to sort of understand what's going on. That's your job, like understanding things. So when this happens, like everybody's natural reaction is to say, oh, well, what's going on with the pandemic? Let me start to become an epidemiologist all of a sudden, and sit in my armchair and do mathematical models and things like that. And I've seen a lot of that with my colleagues. So the natural inclination is to want to understand what's going on, and then also to want to try and do something about it. I realize that my skill set isn't exactly the right the right one for doing that. But I did when this started, I did tell my research group here, if you want to go off and do research on COVID-19 instead of your usual quantum physics, go ahead and do that. And I also did try to start a website where I collected links where people could help with research, like scientists. Because I think that, one of the things that we do is we, physicists and mathematicians in general, we're pretty arrogant guys, right? We think that all the other sciences are like easy, and we could do a much better job. So the natural reaction is to say, oh, they're doing mathematical models. I'm a physicist, I can do a better job. But I think we're better off like working with the people who are actual experts on the topic. So there's a lot of ways of doing that. So I started a website called docovidresearch.org, and that's supposed to be collecting links where you can help out with research. It's really primarily designed for scientists to go on, and it's a wiki. So if you find out of a link where, as a scientist, so, as a scientist, so I mean, like, if you have some expertise in computing, numerical simulations, things like that, you can find out places where people are looking for help. And that's pretty much all I've done on that. Otherwise, things are kind of, I'm keeping things, I'm keeping close to like my core expertise, which is quantum physics and the nature of reality, mostly. We're just trying to get on with what we were doing before the pandemic started.
Yeah, I mean, I was trying to look up and research and take in as much information on I'd say physics. It's a thing people have been able to teach in schools and people can comprehend, but once you get down to the quantum theory and quantum physics, it's like you said, if you don't understand it, that's okay. It's just completely I don't know how to say it. A completely whole new world of rationale. And what you're saying?
Well, yeah, I mean, there's a few things I'd say about it, right? I mean, quantum physics has a reputation, maybe a bad reputation, of first of all being amazingly difficult to understand, and secondly, of saying like really crazy things, crazy sounding things. So in the popular science press, you'll read things about quantum mechanics, meaning that there are multiple parallel universes, or that there are influences that travel instantaneously across space, or nothing's real until you look at it. You'll see all these things written. And I want to say that the key thing to know is the uncertainty principle, right? So you've heard of the Heisenberg uncertainty principle, probably.
Yes, and that was exactly what I'm going to go to next. To be
But
able to harness uncertainty.
I have my own take on the uncertainty principle, which is whenever you read anything about quantum physics, there's a hell of a lot more uncertainty about it than the thing that you've just read. That's my version of the uncertainty principle, right? So it's, the situation is we have this theory, quantum mechanics. It's a very accurate and predictive theory. Pretty much all of modern physics is based on it. But it's 100 years old, so almost 100 years old, and yet we don't really agree. Nobody agrees in physics about what it really means. What does it tell us about the nature of reality? And there's just a great deal of uncertainty about that. And throughout much of the sort of 20th century, at least the second half of the 20th century, most physicists didn't really want to admit that we didn't understand it, or at least that it was an important problem to try and understand it. So there were, there's sort of an attitude of dismissing the questions about the foundations of the theory. And so, that's one of the things that's led to confusion about it. But I think if you just sort of start from the premise that, there's a great deal of uncertainty. And by the way, that's normal in science, right? So most of the big questions that we have in science, we don't know the answers to. And as a scientist, you get used to the idea that, here's a question, we don't know the answer to it. We don't know, for example, the origin of life, ultimately. We don't know, there are many theories about it, but we don't know the exact process by which life started on Earth. That's a big question that we have a lot of uncertainty about, that's been around for, decades and decades, hundreds of years. And similarly, in physics, we don't really know what happened before the Big Bang, right? The problem with quantum mechanics is that because it's a really well-developed theory, we think that we ought to know, and we think we know more than we do. I think most physicists think that we know more than we do, that we sort of understand more about the theory than we do. But I think if you sort of just take a step back and say, well, look, uncertainty is the normal state of affairs in science. That's what we try and do, is we sort of try and approach the questions, rationally, calmly, using the usual methods of scientific inquiry, right? So, you'll read all sorts of crazy things in the popular science media, and they're based on something, right? We know that quantum mechanics is not, as straightforward a theory as classical Newtonian mechanics, right? We know that we can't have as straightforward a picture of reality as you have there, where you have like particles like balls traveling around in space, and that's basically what the theory is about. Well, we don't have that for quantum mechanics. At least we don't agree on what the analog of that kind of picture is for quantum mechanics. So that's a starting point. So you know, people tend to get a bit sort of flustered and panicked when you start talking about quantum mechanics, but you know, I say, look, the physicists don't know the answers. So if you don't know the answers and you're confused, that's good. And the other thing I want to say about it is, I think that the public in general has a better attitude. This is a very unusual thing to say in science, right? Usually the attitude of the public is like, you know, very different from the attitude of scientists. And you know, if you have to pick a side, who's right, is often the scientists. But in the case of quantum physics, the vast majority of the physics community decided that it wasn't really worth discussing the foundational issues in quantum mechanics. But when you write a popular science article about it, that's all everybody wants to know about. So I think the public's right in that context, right? So if you're dealing with a theory where people are consistently telling you things like there are multiple universes and things don't exist until you look at them, of course, why wouldn't you want to be interested in that, right? Why would you not want to try and figure out what's really going on? And so, you know, that's basically the question that I'm trying to address in most of my research. It's sort of like, you know, quantum theory WTF, and let's try and apply the scientific method as far as we can to learn about it.
Well, I think is a quote I heard from it. You know, it's like harnessing uncertainty versus the real world. And once you can harness uncertainty, like, what was it? The coin flip, like someone did a coin flip study where they did it with like the quantum computer versus, you know, everybody trying to guess and how many people would be correct if they were to guess. And because this computer can, you know, harness uncertainty, and because it can move in a binary on a scale between, you know, where we look at it as humans and say it's either going to be heads or tails, but this computer is able to move between on this scale to predict and guess correctly 97% of the time rather than the person being right 3% of the time. I mean, does that have to do with just the way of thinking, or just how these particles and how this area of physics like works?
Yeah, okay, well, I mean, there's several things to get into here. So, I mean, one is just probability, okay? So when you look at quantum physics, the first thing that immediately jumps out at you as being different from physics that came before is the role that probability plays. So, you know, in classical physics and Newtonian physics that you learned in high school, you know, if you know where a particle starts and what speed it's going, you can calculate exactly what it's going to do in the future, and that's determinism. Quantum mechanics doesn't do that. Quantum mechanics only supplies probabilities, and it's silent about anything else, right? So if you set up an experiment in quantum mechanics, then typically what the theory will tell you is, you know, suppose there's a possibility of a particle going to the left and the possibility of a particle going to the right. It will only tell you, it'll tell you, even if you know the initial conditions of the system to as high precision as we know how to do, you'll only be able to predict a probability. So maybe it's a 50% probability of going left and a 50% probability of going right. So one of the questions about quantum physics is, you know, what's the nature of those probabilities? So is it really that there is just some deterministic physics going on, or we just don't know? We just don't know enough, right? Maybe there's a theory that underlies quantum mechanics that would tell us exactly where the particle is going to go, or is it that there's just some fundamental uncertainty in nature, right? So is it sort of irreducible, this probability? We can't get rid of it. There's sort of some fundamental objective chance in nature. So, I mean, there's evidence for both sides. I mean, it is possible to come up with a theory that underlies quantum mechanics that's 100% deterministic. That theory is called de Broglie-Bohm theory, and it's been known about since the 1950s. However, most physicists don't subscribe to that theory for various reasons. One of the important reasons is that that theory has instantaneous non-local influences in it. And in fact, you can prove that any such theory would have to have that. And that's that kind of violates the spirit, at least, of Einstein's special relativity. So Einstein's special relativity, one of the things that it implies is that there's a speed limit in the universe. Nothing can travel faster than the speed of light. So if you have a theory that's positing influences that can work instantaneously across space, then you have a lot of trouble reconciling that with special relativity. So, and you know, you can in fact prove that any theory of that type is going to have instant influences that travel faster than the speed of light. That's Bell's theorem. So you could take that as some kind of evidence that really these probabilities have to be irreducible, but there's, you know, that there are long debates in the literature about, you know, what the meaning of all of this is. So, you know, the bottom line is, you know, again, some people call me the king of uncertainty because of this, but I want to, you know, a lot of physicists would make very definitive statements. They would say, well, from quantum physics, we know these probabilities are irreducible. I would say, we don't know that for sure, but we do know that, you know, either they're irreducible or, you know, or you're going to have problems coming up somewhere else. And this is kind of the way it is. One analogy I like is, you know, we have several different ways of understanding what's going on, you know, several different interpretations of quantum mechanics, right? But it's kind of a bit like, imagine that you had a ball stuck under the carpet, right? You have a ball stuck under the carpet in your house. And what you can do is you can move that ball around from room to room underneath the carpet, right? So I can have the ball show up in the living room, or I can have it show up in the bedroom, but I can't get the ball out because it's stuck underneath the carpet, right? So it's like you can move around where the problems are, where the sort of issues crop up in quantum mechanics, what seems to be the issue with it. In different interpretations, it's different, but it seems like you can't really get rid of it entirely. And it feels like to me that there's still something fundamental that we don't understand about the nature of reality described by quantum mechanics.
Yeah, there's just always so much to unpack, especially when you talk about
Sorry.
the uncertainty and throwing even deeper uncertainty in there, because it's,
Yeah.
you know, you mentioned it's interesting that in, if you want to call it just popular culture, that people are interested in, oh, hey, there's multiple universes out there. Hey, there's, you know, multiple universes. Things don't exist until they appear. And people are having these very, I wouldn't even call them far out thoughts, you know.
Yeah.
I want to say, you know, your imagination is nowhere near as crazy as reality that exists out there. I even think that's a thought Hunter Thompson probably, you know, had said or had before I did, you know. So it's, you know, even the idea of the dream, where it's just like, hey, you start telling someone a dream, and then once you start explaining that dream to somebody, you completely forget what you're trying to explain because of the thing you're trying to even when I'm trying to say it, it makes no sense. So, you know, trying to relay that and present that to
Yeah.
the world has got to be
I mean, one of the things that's often not clear in discussions is that the crazy stuff that you hear, those are mutually exclusive possibilities. They're not all true, right? So one way of understanding quantum mechanics, there are multiple worlds. Well, if you have multiple worlds, then you don't have that things don't exist until you look at them. Because one of the reasons for having the many worlds is precisely to get, you know, to get a picture in which there's a concrete reality all of the time. And so if you have multiple worlds, you don't have that, and you don't have instantaneous signaling. And if you have the situation where things aren't real until you look at them, then you don't have multiple worlds, right? So these are kind of different ways that we've managed to come up with consistent ways of thinking about the theory. We don't know which one's true. I may be in a minority in thinking that there is a truth, right? There is probably a correct way of understanding quantum mechanics. It's just that we don't know it yet, right? What we know, I mean, actually, we've made an awful lot of progress in this subject. It can sometimes seem like it's, every time you hear about it, it's the same thing over and over again. But what we've made progress in, between, say, the 1960s and now, between when Bell's theorem was first proposed and today, we've made a lot of progress in understanding what can't possibly be true, right? So we have an awful lot of negative results. Like, one of the frustrations of working in the foundations of quantum mechanics is not that you can't come up with interesting possibilities. You can. It's just that when you do an experimental test, we always find quantum mechanics is true, right? So it's like you can propose alternative theories, but quantum mechanics is extremely well tested in experiment, and so the frustration is, any idea you have for a possible alternative gets ruled out pretty quickly usually.
So basically, you're just trying to continuously test to find that thing, at least in your case, that proves that quantum mechanics, or there's something else outside of quantum mechanics.
Well, yeah, but it's also a question of where you're going to look, right? So quantum mechanics, or quantum theory in general, or quantum theories in general, they're very well tested in laboratory experiments. Most of our fundamental physical theories are based on quantum mechanics in one way or another. The exception is Einstein's general relativity. You may have read stuff about the fact that general relativity hasn't been combined with quantum mechanics yet. But most of our fundamental physical theories are based in quantum mechanics, so we know it works extremely well up to very, very high energies that we can get to in particle colliders. Everything that we have access to has basically confirmed quantum mechanics. So if you try and propose an alternative to quantum mechanics, and then you sort of expect that you're going to try and test it on a tabletop with some lasers and some optical equipment, it's very unlikely that you're going to see anything other than quantum mechanics, because if quantum mechanics breaks down, it's somewhere where we haven't really looked before. Maybe in the very early universe, maybe in systems that are sufficiently large, contain a large number of quantum systems, things like that. So it's very hard to you have to come up with a specific proposal for not just quantum mechanics breaks down, here's an alternative, but where is it likely or feasible that this could happen? So it's very tough to try and find an alternative to quantum mechanics at this stage. So that's why I'm saying we have a lot of we know that you might think, okay, well, just to give an example, maybe there is sort of an underlying reality which doesn't have probabilities in it. Let's make some list of assumptions about what reality might be like. You prove what the predictions would be for such a theory. You compare it with quantum mechanics, then you can go out and do an experiment, right? So we have lots of results like that, which tell us that really some of the weird features of quantum mechanics are really there to a high degree of precision. And and then the question is, well, how do we understand that? And that's the second part that there's not really any agreement on. The first part, we've actually made an awful lot of progress. We've done a lot, an awful lot more experiments. We know awful lot more constraints on what the nature of reality must be like. So there has been progress, but it's negative progress, if you will.
No, I think I'm starting to get it now. Like looking at that world, like in the probabilities, like when we were starting to unpack back there, you're going into, well, if you believe that things don't exist until you see them, then you kind of can't believe in this idea of multi worlds or, multiple universes, because you'd have to see them into existence, right?
Yeah, I mean, the thing is that, none of these things are assumptions of the theory, if you like, right? So when you're building an interpretation of quantum mechanics, you start from some assumptions, and those assumptions are usually fairly reasonable from a scientific point of view, sounding assumptions, and then you end up deriving the crazy, right? So you start with things that sound reasonable. So to take the example of the many worlds theory, the many worlds theory doesn't start by saying, well, assume there are many worlds. It starts by assuming, okay, well, the theory of quantum mechanics, it gives us an equation. It gives it, there's this thing called the quantum state, sometimes also called the wave function, which evolves in time according to an equation, just like in classical physics, you have states evolving according to an equation, which tells you what's going to happen in the future. And then in comes this concept of measurement, and then you say, well, when I make a measurement, there's this weird probabilistic thing that happens. And the many worlds theory starts by saying, well, let's just throw out all of that stuff about measurements, right? Let's just say that the theory is about this thing, this wave function evolving in time, and that's it, that's the entire theory. And then when you've thrown out the measurement, the postulates about measurement, because the reason for doing that is, of course, the idea of having the concept of measurement as a fundamental primitive in a physical theory is a bit odd. Physical theories usually tell us about what exists and how does it behave. And the concept of measurement is something that's a bit anthropocentric that we've sort of put on top of it, right? This physical device here is a measurement, right?
Mm-hmm.
And it doesn't really seem to have a place in fundamental physics. So in the many worlds theory, you say you throw out all that stuff about measurement, and then you end up deriving, well, that means that there must be multiple universes, multiple worlds, right? So the starting point, what I'm trying to get at here is that the starting assumptions are much more sort of reasonable and rational sounding, and then you derive something crazy. And that's true for sort of all of these approaches, right? And in some ways that's not unusual in physics, right? Because if you think about Einstein's relativity, I don't know how much you know about that, but Einstein's relativity starts from reasonable postulates. There are two of them. One is that physics looks the same regardless of how fast you're moving, right? So you probably had the experience, if you're on a train and the train is going along at some speed, so constant speed, if you throw a ball up in the train, it'll land back on your hand, right? It doesn't feel the fact that you're going at a very fast speed, right? You might expect, if you think about it naively, that the ball should go, back over your head, but it doesn't.
Well, it's like watching any other event from outside the train as well. Nothing is moving any faster or different because you're viewing it as you're moving 80 miles per hour.
So the laws of physics don't care what speed you're going at. That's the postulate number one. And number two is that, however, the speed of light is the same regardless of what speed you're going at. So you might have thought that, if I shoot a laser beam standing here, and you're on a train going by me, that you would see the laser beam going slower than the speed of light because you're catching up with it. But Einstein says that's not true. And the reason why he says that's not true is because we had the equations of that light obeys, called Maxwell's equations. We have the science of electromagnetism. And in the science of electromagnetism, you derive what is the speed of electromagnetic waves. Light is a kind of electromagnetic wave. And you derive that, and it tells you there's this number, 3 times 10 to the power 8 meters per second, very, very fast. And that number doesn't seem to depend on what velocity you're going at. So this was a big puzzle around Einstein's time. And Einstein just said, well, let's just make both of those things true. Physics doesn't depend on what speed you're going at, and the speed of light is the same according to everybody. And you think, well, that doesn't make any sense. Seems to not make any sense. They seem to contradict each other. But the resolution was to say, well, actually, you were wrong about the nature of space and time. If we change, so normally in Newtonian physics, we think of like space and time as two separate things, and space is fixed, the distance between 2 points is always the same, doesn't depend on how fast you're moving and things like that. And Einstein managed to show that, well, if you assume these two postulates, then the way to make them consistent is to say, well, actually, you're wrong about the nature of space and time, right? So if you're going on the train, then you will see the distance between, you'll see the length of an object. If I'm holding a ruler and you come past me on a train at a very, very fast speed, it'll look shorter to you than it does to me. And that idea that we change the nature of space and time allows us to have those things be consistent. So, this is a pattern here, right? We start with scientifically reasonable hypothesis, like the idea that physics doesn't depend on what speed you're going at. That's something that we can experience. We it's an empirical fact. And the fact that the equations that govern light tell us that the speed of light is always the same, that's a fact that comes from the theory. So those are both reasonable facts. So we start with reasonable facts and then we derive the crazy. we derive the crazy. So, the various interpretations of quantum mechanics are a bit like this, right? It's not that we're, a bunch of weed smoking hippies who like to consider like the craziest things about reality. I mean, some of us might be, but we look at what our theories are telling us. We say, okay, well, here are what seem to be scientifically reasonable hypotheses to make about it. They seem a little bit contradictory. Let's see what has to happen to make them true, and then you end up deriving crazy sounding things like multiple worlds. But the difference between quantum mechanics and relativity is that in relativity, we know what the correct reasonable hypotheses to make are, and so we know what the correct crazy conclusions are. In quantum mechanics, we have multiple different alternatives and no agreement about which one's right. So the crazy stuff that you derive is just sort of dependent on your starting point, and people are sort of fundamentally disagreeing what the theory is really about. And that was
that is all fantastic. It's just like unpacking in the midst of a podcast.
Yes.
So
Sorry.
no, this is all amazing. In terms of Einstein's work and and I would say unpacking the different theories, that was an interesting one about physics being the same at whatever speed light is moving, or light is always moving.
Whatever speed you're going at.
Whatever your speed is going, that physics or determinism physics, Newtonian physics stays the same. But once you get out,
quantum mechanics quantum mechanics too. We do have relativistic versions of quantum mechanics, which are compatible with Einstein. What that means though, is that when we look at the predictions, so when we look at, the formalism of quantum mechanics allows us to make predictions for what's going to happen in an experiment. We get a probability at the end of the day. And if you look at those probabilities, they won't allow you to tell how fast you're going, right? So those, the things that we can actually predict from quantum mechanics won't allow you to determine, let's say that you're going at 10 miles an hour and I'm stationary here. There's no sort of preferred speed. The question is just whether whatever underlying quantum mechanics, whatever underlies those predictions, also obeys that, right? And so there's disagreement about that. And this has, this is the issue of whether there's non-locality in quantum mechanics, and gets us into Bell's theorems and things like that.
So I think another thing to be unpacking like more things that you guys get to look at quantum mechanics. So as of my understanding, not until 2015 that black holes were still theories, and until we could read those certain waves that were emitted when those two black holes collided, were we able to actually say that, actually see a black hole or understand that it's real. It was still kind of a theory up until that point. In terms of like how it's looked at and perceived in space, that we see that predicting a black hole is there and could be there.
We had very good evidence for the existence of black holes prior to that, because you can basically tell how an object is gravitating, how the gravity of an object is working, by looking at how other objects orbit it, right? So we had pretty good evidence for a long time that, for example, there were black holes at the center of galaxies. What we didn't, so what was detected in 2015 was gravitational waves.
That's it.
And gravitational waves is a prediction of Einstein's relativity. It says general relativity, this is, so his theory of gravitation. It says that, gravity, well, it predicts that there are gravity waves in a similar sort of sense that in the electromagnetic field there are waves which are light waves, right? So it predicts that, if you have a violent gravitational event, like a collision of two black holes, that radiation is going to be emitted, gravitational radiation is going to be emitted. But gravity is by far the weakest force out of all of there are four forces that we know about in nature. There's electromagnetic force, strong nuclear force, the weak nuclear force, and then gravity. And gravity, it seems a bit strange to say this, because gravity is the force that you're most immediately aware of, right? Why are you sat in your seat now and not floating off into space? It's because that's gravity. But if you think about it, it takes an object the size of the Earth, which is absolutely ginormous, just to keep you down in your chair. And you can actually pretty easily overcome that by, you can jump up in the air. But the gravity is not so strong that it pulls you to Earth straight away. Whereas if you take a comb and you brush it through your hair, I have like the crazy Einstein hair right now because of the pandemic, but if you brush a comb through your hair, it can pick up the electric force can pick up small pieces of paper easily, right? So something small like a comb, right? The electric force on that can overcome the gravitational force of the entire Earth. You think about it. So gravity is extremely weak, right? So if you have just two small pieces of paper, there's a gravitational pull between them, but you can't feel it. It's tiny, tiny, tiny force. So the point is that gravitational waves, similarly, are going to require, in order to be able to detect them, they're going to require like a really ginormous gravitational event, right? That's why you need, because gravitational waves exist for all objects that are moving around, but they're so tiny, right? So it was a massive technological achievement to be able to detect them at all, and very worthy of the Nobel Prize in 2015. And it does, so we're entering a sort of a new era where we can have evidence from gravitational waves as well as evidence from other more conventional things. So we can point a telescope at the area where the gravitational wave signals come from and look at radio waves. We can look in the optical spectrum, and we can see the same events happening in the sort of gravitational wave detection and in ordinary sort of optical astronomy. And this sort of gives us like it gives us sort of another way of looking at things. So that's one of the reasons why it's exciting. Like in astrophysics, whenever we've sort of opened up a new way of observing things, we've learned a lot more. So, initially people only looked at things with telescopes, so we could only see light. But then we had, radio wave astronomy, microwave astronomy. And as you expanded the ways that you have of looking at things, you can see more, right? So being able to detect gravitational waves is, although it's sort of very early days, it's very exciting because, we typically learn more about the universe when we can look at it in different ways. And looking at it gravitationally is very, very different from looking at it in optical electromagnetic ways. So yeah, so that was a very, very exciting thing that happened in 2015.
Yeah, it's like we get to look at the universe and like different filters now. Like, oh, let's
Yeah,
add this filter on top. We can see this now, and see this, and see this. And but I think for most people, even the lay person that who I believe I am, it's like and I think you went into this too. But can you go into a little deeper? Like what about that understanding, benefits people? What about this understanding that you guys are working on your research, actually transitions over into the real world and, the world that we all live and enjoy?
yeah. So I have to say this is okay. This next bit may sound a bit pretentious, but by and large, I'm not too worried. I'm not too bothered about that myself, right? So as physicists, why do we study these things? We study them because they seem very interesting and they seem to be telling us something fundamental about the nature of the universe and our place in it. And so my knee-jerk response to that is just that, well, we want to know these things because that's part of being human, to try and understand the world around us. We want to know these things for the same reason as we appreciate a music concert, right? It's like what benefit does that have? That doesn't have much practical benefit, but we see sort of beauty in it or whatever. Okay, so that's but that is a bit of a pretentious answer. I mean, in some sense, it's my real answer, but governments spend billions and billions of dollars on science every year, and they wouldn't be doing that if there wasn't an economic and societal benefit. Now, when it comes to like real sort of fundamental science, you have to understand the game that's being played here. So the game is it's sort of a high risk, high reward gamble, right? So when you're doing fundamental physics or fundamental any science really, you're going to have hundreds and hundreds of people studying it, and they're all going to have different ideas, and they're going to go and investigate them. And probably 99.99% of that is going to lead to absolutely nothing, right? So lots of those ideas will just be wrong, and some of them, even if they're right, many of them, even if they're right, would just not be useful. It's like, well, you could in principle build a new type of refrigerator out of this technology, but it would be a lot worse than current refrigerating upgrades. So you find out things like this. So that's the game, because you don't know what you're doing when you're doing fundamental sort of science. You don't know, you can't predict the future. So you just throw a lot of ideas against the wall. But then, occasionally there's some idea comes along which really revolutionizes things. And, the gamble that you're playing is that, you hope that happens. And, it has happened time and time again in the history of science, right? So when people discovered electromagnetic radiation and the rules of electromagnetism, nobody knew at the time that would lead to the electronics revolution, and that it would be the technology that underlies all of our communications and all of our computers, modern day computers, right? So this is the kind of gamble that we're playing. So when we're talking about the foundations of quantum mechanics, the specific things that I'm doing right now, what's the probability that will lead to anything practical? Very, 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 very extremely tiny. But I have faith, or at least I think it's a rational view to take, that if we have a decent number of people doing these kinds of things, it will lead to changes, in important changes in technology and society. Now, I guess what you were probably leading towards was talking about quantum technologies, and this is kind of an interesting story, right? Because it's an example of this, right? So quantum technologies, quantum computing, quantum information, they're currently quite big news. As far back as in recent history, in the early 90s, there were half a dozen people in the world who cared about this. And why were they studying it? Because they found that there were interesting questions about the fundamental nature of information, like what is information? And they were interested in those questions. And so it was like really esoteric theoretical reasons that they were discussing these. And it's grown from that sort of small seed into a huge thing that currently, there's currently many billions of dollars going into research in this area. So, I view this as kind of like a success story for the foundations of quantum mechanics. Like, people thought this was an esoteric area, but it has led to big things, the impact of which is really not been felt yet, because we're still a long way from really practical technologies. So you probably want to talk a bit about what that is and what it means.
Well, I think one of the big ones that's happened and come out is that like at least quantum information has been used in cryptography. And I know how big crypto and cryptocurrency, or even just the idea of cryptography, which is masking and creating so many probabilities, different chains or messages or passwords that can be sent out, has been used a lot since that time.
So let's talk a little bit about cryptography, because that's one of the, I think cryptography, even though it's not the whole of the subject, it is certainly one of the reasons why governments in particular have been very interested in it. There are national security implications to cryptographic technologies. So let's talk about this a little bit, right? So suppose, like, the basic problem in cryptography is, say I want to send a message to you. I want to send it to you in such a way that anybody who intercepts the communication can't determine what the message is at all. But when you receive it, you can read it. Okay, that's the basic problem that we have in cryptography. And, so the study of cryptography, I guess, starts in the 1940s. Well, cryptography is a very old subject, but in terms of like formal mathematical studies, Claude Shannon, who's one of the founders of information theory, began studying this during the Second World War and published very important papers on it. And he basically showed that it's impossible. Right? So he showed that it's impossible for me to send a message. Like, if you and I have never communicated in the past, it's impossible for me to send a message to you in such a way that nobody else could also decrypt it, right? So the only way we can do it is, when I say impossible, I mean, let's assume that everybody in the world knows the same stuff, and that we don't have any limitations on how much computing power or whatever we have. So what do you do in the face of that? There's sort of two kinds of things you can do in the face of that. So one is, we can imagine that we actually do share something. Okay, so let's share some secrets. Okay, so if you and I want to communicate, we could get together in a private room somewhere, and we could share some information. Okay, so we could take a bunch of coins and flip them, right, and generate a string of heads and tails, very, very long string of heads and tails. And we do it together in a private room. We assume that nobody else has access to it. And then we go off on our own ways. And now we can use that string of random string of heads and tails to communicate privately. What do I do? Okay, well, I don't want to get bogged down into too much details, but we can say, okay, well, heads equals 0, tails equals 1. So let's convert that into a string of bits, 0, 0, 0, 1. It's a random string of bits. If I want to send you a message, I can also convert that into a string of bits, because I just need, I can convert any message into a number, using ASCII in conversion or whatever. I can just assign a number to each letter of the alphabet from 1 to 26, convert that into binary. I make my message into one long binary string. And then what do I do? If I take the string of heads and tails, and I flip the bit from 0 to 1 and vice versa if it's a heads, and I do nothing if it's a tails. Well, you can see that if you do that, the thing that I end up sending to you is just a completely random string of zeros and ones. No, it contains no information about the message, because all the information about the message is in the correlations between the string I've sent you and the string of heads and tails that we generated. And then you can decrypt it. So this, I don't know if that explanation was very clear.
No, it is. I have a good basis of knowledge of how that happens and how people are trying to do that with banking and
Yeah, so
currencies.
this is called the one-time pad, and it's like it's really the only method of secure communication that's what we call information theoretically secure. It means it's just secure regardless. You don't have to make any assumptions that the eavesdropper has limited computing power or anything. Like anything they could do, they couldn't decrypt this. And in fact, this was used quite regularly for communications between spies during the Cold War. There's quite an interesting story about this. It's sort of fascinating to me. I don't know if you're aware of the history of number stations. Have you heard of it?
No, what's this?
So during the sort of Cold War years, there were these weird radio stations that would just come online for short periods of time, and you can find recordings of them on the internet. They're really creepy. Typically, they would like start with some electronic sounding tune, and then it would just be a string of numbers generated by an electronic machine with like a really creepy voice and in different languages. So it would just be, so the machine would go 9, 7, 6, 5, and these radio stations would come online, and they would broadcast this message, and then they would go away. And so, of course, these were a favorite topic of conspiracy theorists at the time, what was going on. Well, now we have a pretty good understanding from, I don't want to go into too many details, that these were basically one-time pads. And I don't know if you've watched the TV show The Americans at all.
No, but I know it's on FX.
Yeah, so they do this in there. So they get encrypted messages. So they have like a shortwave radio, and they get out, and you can hear the broadcast on the number stations, and then they're decoding them. So what was happening was that spies were given books with huge, long, random strings of numbers in them. So they were generated randomly. And so at home base, they had this book, and the spies had this book with them, and they had a small shortwave radio, and they were tuning to these number stations. These number stations were broadcasting a seemingly random string of numbers, but using the key that they had in their book, they could decode the original message. And we can, there's much evidence that that's what they were. But one of the main reasons why we can tell that is because they pretty much disappeared. They disappeared, when the internet happened, and they disappeared, largely when the Cold War ended. So, there wasn't as much need for them. Anyway, so that was a bit of an aside. But the point of the story now is that, okay, so what can you do? Well, yeah, there's a problem with this, right? Because if you want to do a secure communication like this, it means that we have to get together at some point, right? Somehow you have to get this book of key to the spies out in the field, right? Mm-hmm. The most secure way of doing that is to have everybody gather together in the same room and just generate the random numbers there, and then everybody goes off their separate ways. But what if you've got, somebody who's in the field for, decades, and they've run out of secret key? It's going to be risky to bring them in to do that. So the question is there a way of generating these random numbers in such a way that nobody else could know them? Only the two people who are communicating can know them, without getting together. And this is where sort of quantum mechanics comes in, because in classical physics, the answer is no. There's no way of doing that. That's basically what Shannon proved. You can't do it. But in quantum mechanics, we can. This is what we do in what's called quantum key distribution. So it turns out that by sending quantum systems, so if you have what's called a quantum channel, so this is it could be just, well, it's just a way of sending quantum systems between two people. Okay, so if you have that ability, then you can generate this random string of numbers in such a way that if anybody else tried to read it along the way, then you would know, right? And so you could throw away that set of numbers. Like, we know we can't use that one because somebody else knows it, right? So this is a way, this is one of the applications, the main application in quantum cryptography, and it's actually the quantum technology that's sort of closest to being practically usable today for something actually potentially useful. So that's quantum cryptography, that's quantum key distribution. And so obviously, having the ability to share secret messages with no possible way of breaking it is something that's of great interest to lots of people, and has also national security implications.
No, I imagine governments, banks. I mean, if you can send something, it's
Yeah.
one of the big proponents of, like the cryptocurrency, which I'm familiar with, is that, oh, it's supposed to be the safest and secure transaction, but like you said, it still needs to know that only one person has this set of key and the other person has the same set
So
of key.
I want to talk a little bit about the other way of doing this, because
Okay.
that's also important. But I have to say, the problem with it right now is it's slow, right? So we're at the edge of what we can do with technology, and if you're trying to do this to secure your credit card transaction on Amazon, well, first of all, we don't have the quantum internet yet, but even if we did, even if we had everybody connected by quantum channels, it would be far too slow. It would be like worse
That's a
than
big problem. That's the
worse,
biggest problem. Everybody complains with that.
yeah, worse than going back to dial-up internet. So you can use it for some things, and there's been successful demonstrations, right? So I would call these things sort of more demos than practical things, but several years ago, Switzerland, because Switzerland has one of the main players in this area, a company called ID Quantique. They did a demonstration where they used it to secure election voting. So that's it was more of a demo than a real practical use, but that technology is really beginning to get there. But let's talk about the other side of it. So the other side of it is okay. So most of us don't have the ability to get together and generate these random keys. So what do we actually do in practice? We use what's called computational security. So the previous one was called information theoretic security. So whatever an eavesdropper do, even the most powerful computer devices, unlimited computing ability, couldn't crack it. But we can't do that because we can't all get together and share these keys. So we use what's called computational security. So most cryptography, including Bitcoin cryptography, is based on this idea of public key cryptography. And the idea there is you try to come up with a mathematical problem that's easy to do one way and hard to do the other way. Okay, so the simplest example is factoring numbers, right? So if I tell you to multiply 27 times 36, okay, maybe, I don't know if you can do it in your head, but it's a relatively quick calculation to do.
900. No, I'm
Okay.
off. I was going for 30 to 30 seconds.
If I say, what's 15 times 3, right?
45.
Right, okay, you can do. But if I asked you, okay, what are the factors of 58, right? What times what is 58? It takes you a lot longer to do, right? So you have the intuition that here's a problem that's easier to do one way than it is to do the other way. Okay, so and in fact, you can make this sort of more formal and say, well, let's try and make a computer do this. So if I take any two numbers and want to multiply them together, then I can do that on a computer efficiently. If I take a number and ask what are its factors, then the best computer algorithms that we know typically take a very, very, very long time. Okay, so the idea of public key cryptography is that you have right? So you have, well, okay. So you have, the idea is that, okay, so you have two things, right? You have a public key and a private key, right? So if you want to communicate to me, I will give you my public key. And the public key is something which is sort of easy to compute. It's like, it's something that's an easy computation. If you don't have the private key, then to decrypt that message, you need to do a computation which we think is hard, okay, which would take a really long time. And you need this private key. So this private, so like the public key would be something like, take these two numbers, multiply them together. That multiplied number is the public key, and the private key would be the two individual numbers, right? So it's hard to determine the private key if you only know the public key. And it turns out that there are methods to use this to send secure messages, and which we think would be very, very hard to decrypt. Like, you just would take longer than the age of the universe to run a computer algorithm to decrypt it. So that's the idea here. So it's not in principle impossible to decrypt the message. It's just that we think it would take far too many computational resources. And that's what most cryptography that we use, or all cryptography that we use on, say, the internet and for Bitcoin, is based on this kind of idea. Okay, so that's how it works. And now the fly in the ointment here is that we have this idea of a quantum computer, and a quantum computer is a computer that operates according to the principles of quantum mechanics, right? It's just a computer that's made of quantum systems. We have these quantum bits called qubits, and they interact. And there's an algorithm which allows you to break many of these crypto systems. So the assumption that factoring numbers was hard is true, seems to be true for classical computers, but if you had a quantum computer, you would be able to break it easily, right? So you know, the quantum technology has two sides to it. So one is, it does give us a method of doing a secure kind of cryptography, but it also breaks much of the cryptography that we rely on today, right? So if we were able to build one of these full-scale quantum computers, then we would have problems with current crypto systems.
So they're going against each other, or the push for one is going against the.
Well, the push is for both at the same time, of course, right? Because the one now the other thing I have to say is that this is true of current. So one of the crypto systems that is used a lot is called RSA. RSA is the one that's based on factoring numbers. That would definitely be broken, but another field of research that's popped up in recent years is something called post-quantum cryptography. So this is the idea that you try and come up with public key cryptography systems that are not vulnerable to attacks by quantum computer. So several of these have been proposed. And so we think that there are probably public crypto systems, just classical ones, which would be robust against quantum computers. But we don't know that for sure, because one of the ways that cryptography research works is, quite often you are unable to prove what you'd like to prove rigorously. Prove that it's very, very hard to break RSA cryptography. You can't really come up with a proof of it.
Yeah.
What you do though is you let hundreds and thousands of researchers loose on it, and they try to decrypt. They try very, very hard to decrypt it over a number of years. And the more times we fail to do it, the more confident that you become that it really is a good method. So post-quantum crypto systems, we believe that there probably are classical crypto systems that are robust to quantum attacks, but they haven't been around as long. So, we don't know if they're really vulnerable to some very, very clever attack. So that's kind of a topic of current research. But it seems likely that by the time that we have quantum computers, things like RSA will be replaced by things that are secure against quantum computers without having to go to full-blown quantum cryptography.
This I can digest. This,
yeah.
that made sense.
But however, you know, we're in a funny situation with this technology because um, it's, I find it, okay, so, you know, I don't want to digress too much on politics, but um, funding quantum technology is one of the very few scientific issues that has full bipartisan support in the United States, right? So a year or two ago, Trump signed a bill called, I think it was called the Quantum Initiative, sailed through Congress, provided billions of support for these technologies.
And that never happens.
It never happens with a scientific issue, right? Think about funding for climate change or vaccine research or whatever. Like, these things are very, very controversial in the current situation, right? The sort of widespread, you know, bipartisan support for every scientific issue just isn't there in general. But there's a few things for which it is, and quantum technology is one of them. So, you know, you have to wonder why that's the case for this. And you know, the uses of the technology extend beyond cryptography, but you have to think that as far as governments are concerned, as far as the US government's concerned, the national security part of it is important. And also playing a major role in this is the fact that the Chinese government has decided to spend a lot of money on this area. Okay, so we seem to be sort of transitioning from a period where this was sort of a usual scientific international cooperation type of topic to things are sort of starting to transition into a slightly more adversarial situation. Most scientists don't want this to be the case, but it is nonetheless the case that Chinese scientists who are hoping to come here to the US who have expertise in this area are now finding it hard to get visas to come. And the US government is looking hard at people like FBI and CIA and organizations like that are beginning to look at people who have ties to research institutes in China. That's just happening, right? So whether we like it as scientists or not, this is the kind of attitude that's being taken here towards this technology. And there is one fear, there's one thing which I would say is a reasonable fear, which is that although we will probably have changed to more secure crypto systems by the time we get a quantum computer, there's historical data, right? So, you know, we know from the Snowden revelations, for instance, that the US government likes to collect, the NSA likes to collect massive amounts of data. And you can assume that the Chinese government also collects massive amounts of data. You know, so there might be a store of encrypted email communications somewhere on a server that someone has that they can't decrypt, right? From today, right? Say when we're still using RSA encryption. And in a couple of decades, maybe we'll have a quantum computer and suddenly they'll be able to decrypt that stuff. So, you know, although it might be a sort of a second order worry, you know, you do worry that maybe there are some, say, dissidents in China who are using encrypted email technology, and maybe in 20 years' time, the government will be able to decrypt those. And so I'd say, you know, there is a legitimate concern about that sort of thing. And as scientists working on this, we have to, you know, start considering very carefully what are the ethics of doing this kind of work. And we should be thinking harder about sort of ethical frameworks for the research we're doing, especially as it relates to cryptography and national security. Because I just don't think that we're going to go back to a time where this is all happy international cooperation, right? The US government, the Chinese government don't seem to want to go there. So the reality is there are going to be restrictions, there are going to be you know, problems, there's going to be a certain amount of adversarial competition in it. And you know, as scientists, how should we ethically deal with that? I think that's something that we, you know, we're only just beginning to think about.
No, it's crazy. I mean, I think about immediately when you talk about this is when we think about the an arms race, or any R&D that goes
Yeah,
towards the defense, and you think just the race for the atomic weapon and
yeah,
the atom bomb, and the physicists getting in the way, were saying like, hey, morally justified. Was it Oppenheimer constantly going with the what was his name, the one of the head of the defense departments, and he was just going back and forth with them, back and forth with them. We can't, this
yeah.
is
Well, I
moral.
mean, I think in physics especially, like anybody who's read the history of the Manhattan Project, anything about it, you know, the idea that scientists are sort of morally neutral and it's like we just do the science and everybody else worries about how it's used. The history of that project should show anybody that that's not the case, that's not viable. So I think physicists more than anybody else, given the role in atomic weapons, should be sensitive to these kinds of issues, even if the risk is like fairly low. We should be sensitive. But I'm in two minds about this. It's not clear. Like there are two sort of big examples that you have in mind. You have the Manhattan Project, of course, but also the space race, right? So the two are kind of different. The Manhattan Project was, an issue of immediate urgency and military application. The space race was kind of like a race for prestige. So who's going to get to the moon first, America or Russia? Does it really matter to the future of our military survival who does it? No, it's a matter of national prestige.
Right.
So I think a lot of people are arguing that China versus the US in quantum technology is something more like the space race. It's a bit different because the space race was done almost entirely by governments, whereas in quantum technology these days private industry is a very, very big player, right? So you have companies like Google and IBM and even Alibaba in China involved in this. So it's slightly different, but I think most people think, well, the risk that this is going to have a major national security application is actually pretty low, and it's more a question of, it's a race for prestige. And certainly China, there's an argument for that. I mean, certainly China has decided in recent years to try and become much more prestigious in the scientific realm, right? So, decade or two ago, most Chinese research was not of the greatest quality, should we say, right? So, I mean, I'm not trying to cast aspersions, but if you found a scientific paper published, say a decade or two ago, which had all Chinese authors from all Chinese institutions, it was a good indicator that it wasn't going to be very high quality.
Mm-hmm.
Just because, the Chinese government wasn't funding things appropriately and Chinese scientists had a very hard time doing good work. But they've changed their attitude massively. They're now trying to, it's a matter of national prestige to have good science. And also, since China is basically the manufacturing zone of the world now, previously they were operating in a mode where, they took intellectual property, they took designs and science which had been come up with in other places and then manufactured it. But it obviously makes a great deal of sense for them to own also the intellectual property on which these things are based. Mm-hmm. So the race for dominance in quantum computing is definitely part of this, and the fact that the Chinese government has decided to put a lot of money into scientific research now is part of it. It's a play for national prestige. It's all of these things. Now there is this national security implication as well. So I don't think that we should completely dismiss that. So I'm going to say this isn't exactly the Manhattan Project or the space race.
Way more space race.
It's a bit closer to the space race with a little bit of Manhattan Project in it. And so I think that because people think it's more like the space race, a lot of scientific organizations have made calls for continuing international cooperation in this area in the face of what's happening now. I think it's a little bit naive to expect that governments are just going to, roll over and agree with that, because the national security argument is an argument that's been made, and it's either the scientific community has overhyped the uses of quantum in technology, in cryptography, in which case the governments are going to be angry with us for wasting money on it, or we haven't overhyped it and it's a real concern. I think it's the latter, personally. And so I don't think that, I just don't think that things are going to go back to the way they were, and it's something that we have to deal with. So as far as what the everyday person should be aware of about quantum technology, if you're interested in cryptography at all, and the issues like privacy and security, it's something to be aware of. This is coming, right? It's coming, whether it's coming, probably not coming tomorrow, but it's coming within the next couple of decades.
Well, I think if you're an American and you actually care about security, privacy, freedom, so to say, you really follow those Bill of Rights, especially that First and Fourth Amendment, to understand, search and seizure, understanding what can be owned, what can be seen, and what can be divulged to, your government or authority. Those are definitely things you should be interested in going into, because it's like an evolution of, those original rights, the right to privacy, the right, so we have a right to privacy, but, right to free speech, the right to search and seizure, and this is where it's evolving and moving towards, and it's, of all places, moving on the quantum mechanic level into cryptography.
And we should certainly, although, arguably the implementation of rights and freedoms in the USA is not perfect. I don't think anybody would argue that it's perfect.
No.
But we should definitely be concerned about whether the major technologies and discoveries happen first in a country like the US, which has those kinds of freedoms, or whether it happens first in a country which is largely authoritarian and which does not grant its citizens those kinds of rights and freedoms. And I think, that's something that, that as scientists we should be concerned about. So, I don't want to say, I have many colleagues who collaborate with scientists in China and internationally. I'm not trying to tell anybody, that this has to go, this whole area of research now has to go on lockdown. What I am saying, though, is that we need to think about the ethical frameworks for how we go about maintaining a global approach to the science, while taking these kinds of issues into account.
Matt, no, that's all fantastic. And I wanted to thank you for coming on the show. I definitely hope to have you back, and I hope, I myself going to go back, unpack, and listen to all this stuff again, go back through all your notes and stuff. And whoever's listening, please let them know where they can, see all your information, have good places to research, find things. I know you mentioned a few of those things would be on your website. But if you can go ahead and let people know a little bit more about where they can connect with you and see some of this information.
Okay, well, first of all, thanks very much for having me today. So my website is mattleifer.info. It's mattleifer.info. I'm on Twitter at Matt Leifer, and Facebook. I believe it's Matt Leifer on Facebook too. So you can connect with me in those places. Also, if you're interested in the website I have about helping with COVID research, that's called docovidresearch.org.
And I'll make sure I have a link to those all in the bios in there. Thank you again for tuning in, and thank you for joining me on the show. Looking forward to having you back. Definitely will be a return guest. And to everybody who's watching this on the live stream, thanks so much for tuning in. Go ahead, subscribe to the channel. We have another show coming up in about 30-45 minutes. I'm going to go get ready for that one. And if you're watching this at a later time, thanks so much for tuning in. Thanks so much. And if you want to support the show, there's plenty of ways to do that. If you want to support it, just keep watching and suggest more amazing and very cool guests to have on the show. And that's about it. Matt, thank you. And thank you, everybody, for watching. Have a great day.
Brandon.
Left.